The next p-value pitfall we're going to talk about is something called the problem of multiple testing. This problem is best illustrated with an example. This is one of my favorite studies in the medical literature. It shows why it's great to be a statistician. So this is a 1980 study. Some researchers at Duke University randomized about 1,000 heart disease patients into two groups. And that was the end of the study. See, it's great to be a statistician. You don't have to do anything too hard, right? They just randomly assigned those patients to either group 1 or group 2. Essentially, they put their names in an Excel spreadsheet as whether or not they were in group 1 or group 2, and then the study was done. This means that we know for sure that there is no biological effect here. We know that being in group 1 can't have done anything differently than being in group 2. We know that the null hypothesis is true because that's all. There was nothing done differently to the two groups other than where they ended up in the Excel spreadsheet, which obviously would not affect their outcomes. So this is a case where we know that the null hypothesis is true. Then the researchers tracked the survival of those heart disease patients, and not surprisingly, there was no difference in survival between group 1 and group 2. We'd be really surprised if there had been a difference. But then the researchers went on and did the following. They started to divide the patients up, those 1,000 patients up, into subgroups based on prognostic factors. And in a subgroup of 397 patients who had 3-vessel disease and an abnormal left ventricular contraction, in that particular subgroup, they were able to find a survival difference between those randomized to group 1 and those randomized to group 2, and the p-value was less than 0.025. There was a statistically significant difference in survival between the two groups. But how can that be? We know that nothing was done differently between those two groups. How can we have gotten a statistically significant survival difference? What's going on here? Well, what happened is that if you parse the data up enough ways, so they tried this subgroup, they tried that subgroup, they tried 18 different subgroups. In one of those subgroups, it's not that unlikely that there would just be a chance imbalance. Just by chance, by a fluke in one of those subgroups, we happen to have a little bit better survival in group 1 than group 2. It's a chance imbalance, and we know that the null hypothesis is true here. So we know if we reject the null hypothesis, we know we will have made a type 1 error. You can get imbalances in your data, though, and if you parse your data, if you start hunting around in your data enough times, you will find some statistically significant p-values that pop up just due to chance. This is the idea of the multiple testing problem. Remember, if we set a significance level of 0.05, we're allowing a false positive rate for one test of 5%. That's for one test, though. If you run more than one test, every test has a false positive chance of 5%. If there's nothing going on in your data, if there are no effects, your chance of getting a false positive, if you set the significance level of 0.05, is 5%, 1 in 20. But let's say you run many tests. Let's say you run 18 tests. Then the probability of getting a false positive is much higher, and we can actually calculate what it would be. So if we compare survival of treatment and control within 18 different subgroups, that's 18 comparisons. There's a 5% chance that any one of those, each one of those has a 5% chance of generating a false positive. When you have 18, though, the chance that at least one of those comes up to be a false positive is much, 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 much higher than 5%. And we can actually calculate it using what we learned in the probability unit. How would we calculate that? Now we have to make a little assumption here in order to be able to calculate this easily. We're going to assume that all the comparisons are independent. That's the only way we can solve this easily. Of course, these comparisons are not independent because some of those subgroups would have overlapped. So this is sort of a maximum that we're calculating. But think about the way we would calculate this. What's the chance of at least one type 1 error? Remember, this is one of those at least one problems in probability. Well, every test has what? Every test has a chance of a type 1 error of 5%. So that means it's in at least one case, so what are we going to calculate? We're going to calculate 1 minus the probability of none. Well, what's the probability of none here, of getting no false positives over 18 tests? Well, that's going to be 1 minus, and what's the probability of getting no false positives over 18 tests? Well, the probability for one test of not getting a false positive is 95%. 95% chance you're not going to get a false positive. But we have to do that 18 tests in a row. So that's 0.95 raised to the 18. When you do that and then subtract from 1, it turns out that the chance of at least one false positive is somewhere around 60%. In other words, you're expecting to get at least one false positive when you run 18 tests. It would be surprising. You have a 60% chance. It would actually be surprising if you didn't get a false positive. This is the idea that if you torture your data long enough, they will confess to something, right? You can keep parsing up your data until you find a chance imbalance somewhere. That's essentially what you're doing when you're doing multiple testing. If there are no effects, you should expect to get a p-value of less than 0.05 about 1 in 20 times. That's what that significance level does. It guarantees you a type 1 error rate of about 5%. 1 in 20 times, you're going to get a false positive. If you run lots of tests, you're going to have more opportunities for chance findings. And there's lots of ways that we run lots of tests in statistics, right? Let's say we're doing a study where we look at multiple different outcomes, all these different types of cancer. Well, one of those cancers might come up significant just by chance, or a lot of times we look at multiple different predictors. Or we do subgroup analyses. So it's very typical, for example, in a randomized trial, just like the one I was talking about, where you actually have a drug, though, where you go out and do the randomized trial and it turns out that there's no significant effect overall on survival. But then people start parsing up into subgroups, and lo and behold, they get a statistically significant result in one of those subgroups. And they come up with a great biological explanation of why this drug will work for those with an abnormal left ventricular contraction. They can come up with an explanation, but if you parse your data enough, probably it's just a chance finding. There's also other ways when people are analyzing their data, some of these things are hidden. Maybe they tried a whole bunch of different ways for how to define exposure. Like, how do I define drinking, light drinking and moderate drinking? I can try a whole bunch of different ways. If I try lots of different ways, one of those by chance is likely to come out significant. Or if I do repeated measures, if I look at the outcome at multiple time points, by chance one of those outcomes might come out significant. Or multiple looks at the data, if we're doing a randomized trial and we keep peeking at the data. There's so many places where you can get multiple testing coming in and increasing your chances of getting a false positive, of getting a type 1 error. So I like to illustrate this in my on-campus class with the following little experiment. I do an experiment where I also know that the null hypothesis is true. Just like those Duke researchers knew for sure that the null hypothesis was true. They knew that any significant p-values had to be false positives. I do the same little experiment in my class. So I asked my class to fill out a survey at the beginning of the quarter that says that asks them a bunch of questions. And one of the questions I like to ask is whether or not you were born on an odd day or an even day. Because presumably being born on an odd day or an even day really doesn't have anything to do with anything in your future. So I know that the null hypothesis is true. I know that there shouldn't be any difference, real difference between those two groups. And then I asked the students to provide data on lots of other variables about themselves. In one class, I asked them to provide data about 28 variables. I want to make sure that I'm going to get a false positive. So by doing 28, that's a lot more than 20. I'm kind of guaranteeing myself a false positive. So what I then do is I take the results from all of those variables, I compare people born on an odd day or an even day with the correct statistical test, and then I record the p-value from all 28 comparisons, all 28 tests. And I recorded those p-values from all those tests, and I put them in a histogram so we can see what the distribution of p-values looks like here. Again, we know the null hypothesis to be true because I don't think being born on an odd or an even day affects any of the variables I asked them about. So what do you see here? This is the histogram for p-values. I did 28 tests, and I'm showing you the counts on the y-axis. The p-values range from 0 to 1. It's a probability. It has to range from 0 to 1. So what do you notice here? What distribution does a p-value follow when the null hypothesis is true? It follows a uniform distribution. It is completely random, if the null is true, where the p-value will fall between 0 and 1.0. And notice when you look at this graph, the thing that your eye is drawn to is the following two things. Your eye was drawn to here and here, the gaps. So for some reason, just by chance, I didn't get a p-value between 0.15 and 0.2, and I didn't get a p-value, any p-values between 0.75 and 0.85. It's completely just chance that I didn't get any there. But those are the most surprising things. What's not surprising is that I happen to get two p-values between 0 and 0.05. So this bar here, I got two statistically significant p-values, p of less than 0.05. But if they hadn't gotten any p-values there, it would have been surprising. I'm expecting, because p-values follow a uniform distribution, that I'm going to get some p-values that happen to fall between 0 and 0.05 just by chance. And in fact, you can show that p-values follow a uniform distribution. So what I did, just to show you so you can compare, here's the p-values from my class. Looks like it follows a uniform distribution. When I generate 25 random numbers from a uniform distribution, I come up with similar distributions. This is just showing you that if the null hypothesis is true, you're expecting to get anywhere from 0 to 1 with equal probability. That is, values between 0 and 0.05 or between 0 and 0.1 are not surprising. They're expected. In fact, it would be odd if you didn't get some p-values that were statistically significant at the 0.05 level when you do so many tests. Let me give you another multiple testing example from the medical literature, just show you a real example where I think probably what's going on are chance findings. So this was a study. Researchers were looking at whether or not caffeine and coffee drinking and tea drinking, whether or not any of that influences your risk of breast cancer. There's been some thought in the past that drinking caffeinated coffee and a lot of caffeine might increase your risk of breast cancer. So they did a very thorough study. They asked women about their caffeine, coffee, and tea consumptions, and they looked at who got breast cancer and who didn't get breast cancer. Now, they looked at this in a lot of different ways. They looked at, does caffeine drinking, coffee drinking, or tea drinking, do any of those things relate to getting breast cancer at all? They also looked at breast cancer in multiple subgroups. So the type of breast cancer, they broke that down. They also looked at the type of women. Is it a postmenopausal woman or a premenopausal woman? So they made multiple subgroups. So essentially they ended up running about 50 statistical tests to look at all of these different possible associations. So notice a large number of tests here. Overall, there was no association between caffeine, caffeinated tea, and breast cancer. However, they came out with 4 significant or near significant p-values at statistical significance at the level of 0.05 in some subgroups. So they found that coffee intake was linked to an increased risk of breast cancer in women who had benign breast disease. That's a particular subgroup. The p-value there was 0.08, so not quite statistically significant at the conventional 0.05. They also found that caffeine intake was linked to an increased risk of a particular type of tumor, estrogen, progesterone negative tumors, as well as larger tumors larger than 2 centimeters. The p-values there were 0.02 and 0.02 for those comparisons. They also found that decaf coffee was linked to a reduced risk of breast cancer in postmenopausal hormone users. Notice as I'm reading that, the number of qualifiers that I'm putting in there. When you start having lots of qualifiers like that, that's when you start to worry about things like multiple testing. The p-value there came out to be 0.02. So overall, they found, coffee, caffeine pretty safe for breast cancer, but then they were worried about these significant, I'm putting significant in quotes, significant p-values that came out. And the media coverage reflected that. It said, like, caffeine consumption was associated, they said caffeine consumption overall not related to breast cancer, but it was associated with hormone-negative breast cancers and breast cancer tumors larger than 2 centimeters. But the study did uncover an increased risk of cancer for women with benign breast disease who drank 4 or more cups of coffee a day. Caffeine consumption was also linked to an increased risk of tumors that are hormone receptor negative or larger than 2 centimeters. So in other words, the implication here was that, oh, well, overall, it's not bad. Coffee is not bad for breast cancer, but it does affect these other subgroups, and we're worried about caffeine for those subgroups. However, my conclusions from this study would be completely different. So here's what I did. I went through that study, and this took me some time, but I went through that study. They had multiple tables with all these different results, and they had p-values for each of those 50 tests that I talked about, the 50 different comparisons they did. I extracted the p-values from all of those 50 tests and put them in a little data set and graphed it just so I could see the distribution of the p-values. So notice what the distribution looks like. It looks like a uniform distribution. Remember, if the null hypothesis is true, if there's no effects, we expect the p-value to follow a uniform distribution, equal probability from 0 to 1. Notice that the most surprising thing, as I mentioned earlier, the most surprising thing on this graphic, the thing that your eye gets drawn to, is that there are no p-values between 0.8 and 0.85. That's the surprising thing, that there's a gap. In fact, it would be surprising if we had found no p-values between 0 and 0.05 or between 0 and 0.10. Those are the ones that they mentioned. It would be completely surprising if we found none there. In other words, the p-values that we found that were statistically significant, these moderate 0.02, 0.08 p-values, those are almost certainly, they're very highly likely to be chance findings. They're completely consistent with chance findings. We're going to get some significant p-values. If you do 50 tests, some of those p-values are going to come out significant, but those are most likely just chance findings. You can also look at other things in the paper to kind of convince yourself that these are almost certainly chance findings as opposed to anything real. So I looked at the effect sizes. They calculated risk ratios here. There was no consistent pattern. So the risk ratios, they weren't big. They were all close to 1. They ranged from 0.67 to 1.79. So no big values, no big effect sizes here. And they jumped around from below 1 and above 1. It wasn't like they were all in the direction of harm. There's About half were below 1 and about half were above 1. So that's, again, a pattern that's consistent with chance. There was no dose response pattern when they looked at the level of caffeine. So all of these things are implying that it's almost certain that those significant p-values that they found there were just purely chance findings, and you'd actually expect to get a few significant p-values just by chance here. So what kind of things should you look for if you're trying to decide whether or not something is likely to be a chance finding? So hallmarks of a chance finding are things like the analyses are exploratory. There's a lot of tests that have been run. Many tests have been performed, but only a few come out significant. You've got one significant p-value in the sea of non-significant p-values. Another hallmark is that the significant p-values are modest in size. You have a high probability of just by chance getting p-values between 0.01 and 0.05. But the chance of getting a chance p-value that's less than, say, 1 in 10,000 is very, very small. So very, very highly significant p-values are much less likely to reflect chance findings. But modest-sized ones are very consistent with chance findings. If you see that the pattern of effect size is inconsistent, as I just mentioned, that would be an indication that something might be a chance finding. Finally, there is a way that we can deal with chance findings. We can deal with the problem of multiple testings. We can correct the p-value. There are methods that statisticians have come up with to actually adjust the p-value to reflect the number of tests that have been run. These are called Pvalue corrections. There's some optional material at the end of this module if you would like to have more details about some of those specific ways that we can correct the p-values. Another place this has come up a lot in recent decades is with things like microarray analyses, high throughput genomics. So when you do something like a microarray, you might be comparing two groups, like a cancer group and a control group. And there's usually small groups, but you're comparing the expression of 30,000 genes. That's a huge number of comparisons. So let's say there's no differences between the groups. There's actually no difference in gene expression. If you set your p-value, your significance level, to be 0.05, well, out of 30,000, 5% of those are going to come out to be statistically significant at that conventional level of 0.05. 1,500 are going to achieve that purely by chance. You're expecting that. So there were a lot of microarray studies that came out that were later believed to just be false positive, because you can get so many false positives when you run so many tests. We had to change the way that we actually analyze microarray data to account for that. And it's another interesting question that you can think about is, well, if you just look at the literature, how common are false positives? Now, you might think, well, okay, false positives are 1 in 20, because I just told you the false positive rate is 1 in 20. But you have to be a little bit careful about that, because what I've told you is that the probability of getting a p-value of less than 0.05 if there are no effects, that is, if the null is true, that probability, of course, is 5%. That's your false positive rate when you set the significance level at 0.05. You're going to get a statistically significant p-value just by chance when there are no effects 5% of the time. That's the probability that we know. Of course, to answer the question, how common are false positives in the literature, we want the reverse of that conditional. We're going to have to apply some Bayes rule here. So if I want to switch that, what's the probability that the null hypothesis is true? That is, that the effect is not real if I get a p-value of less than 0.05. That's a harder question to answer. We have to apply Bayes' rule to answer that question. We don't have that probability with the conditionals in that direction. We don't have it directly. And you have to make some assumptions. So you'd have to apply Bayes' rule here and then make some assumptions. And of course, those assumptions can really affect the estimate here. But somebody's done that and tried to make some reasonable assumptions. And one paper said that it turns out that about 1 in 2 p-values under 0.05 in the medical literature is a false positive. In other words, half of all the significant p-values you see out there are just a false positive. That's their estimate based on applying Bayes' rule here. But if you look at p-values less than 0.01, it goes down. Only 1 in 6 are a false positive. If you look at p-values less than 0.0001, then only about 1 in 56 are false positive. So again, those modest p-values, 0.01 to 0.05, are much, much, much more likely to be false positives. If you get a really, really small p-value, it's much less likely to be a false positive. Take-home points here is you've got to look at the totality of the evidence. If there's tons and tons of non-significant p-values, but one significant p-value in a sea of non-significant p-values, don't be that impressed by that. authors tend to want to just jump in and say, oh, I'm going to look in my data until I can find a significant p-value. Well, some of those significant p-values are just chance. So don't be that impressed by one significant p-value out of a sea of non-significant p-values. Expect about one significant p-value in about 1 of every 20 tests if there's nothing going on in the data, if there are no effects. I want to spend just a minute here to mention p-value corrections, because one of the ways we deal with multiple testing is to try to somehow control the type 1 error by correcting the p-values or adjusting the p-value level that we're going to call statistically significant. We call these corrections, p-value corrections, multiple comparisons corrections. The simplest one that many of you may have already heard of, is something called the Bonferroni. It's the easiest one for me to illustrate. It's easy to apply. So I'll start with that one. It's also the most conservative correction procedure. In other words, it's a little bit too conservative at guarding against multiple testing. And what can happen if you apply Bonferroni is you may end up with no statistically significant results as a result. You may increase your type 2 error. But Bonferroni is simple. So if you have just a few tests and you want to do a simple correction, here's what you can do. All you're doing with the Bonferroni is saying, let's say you want to control your type 1 error rate study-wide for all of your tests, not just one test, but all of your tests at a level of 0.05. And let's say you want to run 5 tests. If you want to run 5 tests, one way to keep your overall alpha, your overall type 1 error rate at 0.05 is to require statistical significance to be more stringent. So if you want to keep your overall error rate to be 0.05 and you're going to run 5 tests, you could just divide those two things and say, well, I'm only going to count something as statistically significant, not if the p-value is less than 0.05, but if the p-value is less than 0.01. So for example, if you had obtained a p-value of 0.001, and you would run 5 tests, you would still count that as statistically significant because that is still below 0.01, so we'd call that significant. If I ran 4 tests, then my new significance level would be 0.013, 0.05 divided by 4. You can see how easy this is to apply. You're just dividing 0.05 by the number of tests you ran to come up with a new cutoff for statistical significance. So let's say you got a p-value of 0.011. You want it to be under 0.013 for statistical significance here, so that would still be statistically significant. How about, though, if you ran 3 tests, then your significance level, if you're going to do a Bonferroni correction, you change your significance level to 0.017. So a p-value of 0.019 would now no longer be statistically significant. So in conventional statistical significance, 0.019, we'd say that was significant. But when you apply Bonferroni, correcting for the fact that you ran 3 tests, say 3 outcomes, then that's no longer statistically significant. And so on and so forth. So if you ran 2 tests, you'd need a significance level of 0.025, so 0.032 wouldn't cut it. And if you run 1 test, of course, its significance goes back to 0.05. So Bonferroni is easy to apply, but it's highly conservative because it's actually assuming that all the comparisons that you're running are completely independent, and that's usually not the case. Usually you're running things that are related to one another.